Welcome to What the Fudge. Last time in my previous videos, I went over the fact that that molecules, depending on some things, can exist, as a liquid, as a gas, as a solid, fully, and sometimes in some places, they exist as both a liquid and a gas. So you'll have if you have like one container, you have it as a liquid and a gas. They're both happening. So I went over that the molecules exist partially as a liquid, partially as a gas. I went over that. That's the first video. Watch that. And then in the second video, I went over the fact that how molecules interact with themselves and how and the different ways of doing that, and then how that they also can interact with other molecules. And I said that when different molecules interact, it actually changes the properties of both molecules. Okay, so that's what occurs, and that can cause the point at which a molecule exists as a gas or as a liquid, or partially as a liquid and a gas. That will change when you mix it with another thing, with another molecule. Okay, that's what I said. And then also I said the amount that will exist they will exist as a gas and as a liquid will also change when you add a certain amount of another molecule. Okay, at a certain pressure and temperature. Okay, so I went over that. So in this video, I'm going to show how when you mix two things, the pressure and temperature at which the molecule becomes a liquid or gas changes, and then also the amount that will exist of liquid and gas changes, and the amount that it changes is dependent on how much of the other molecule you add. So I'm going to show that the way people have already gotten this data. Okay, they've already gotten this data, so we're just going to look at the data. So we don't have to do this. This exists. This is a thing. It's proven. We found out what the universe wants. Okay, when you add these two things in the system at this pressure and temperature, we found out what it wants. So now we're just going to look at the data. So it's like this. Make a plot. Okay, and we're going to call this. This is going to be temperature. Okay. And we're going to put, it's going to be Kelvin. Okay. Kelvin, if you know what Kelvin is, I'll go over really quick. Basically, it's another measurement scale like Celsius. Okay. It's like Celsius. But the difference is that Celsius, it's more like a common sense, what's around us scale. This is why it was made, and it was made first. Basically, the Celsius is the guy said, okay, I notice this is the point at which water freezes. Okay, freezes. This is the point at which water becomes fully a gas, right? We went over this last time. Point at which water becomes fully a gas. This is the point at which water becomes fully a solid, right? And then there's that VLE we saw, depending on the pressure and temperature, right? So what he said is that, okay, freezing here, boiling here, I'm going to create the system that says, okay, we're going to call the point at what water freezes at 100 kPa. kPa. We're going to call this the point at which water freezes at 100 kPa. We're going to call this 0. We're going to make this the 0 on the thing. Okay? And we're going to make this out of 100, so that I'm going to make my scale from 0 to 100. Okay? And I'm going to say that 100 is the point at which water boils. And that's it. He just said that he's going to make 100 the point at which water fully becomes a gas, the point at which water boils. So that's what he did. He could have made this 1,000 if he wanted. He could have made this 56. And it's nicer to be 100, right, than 56, because it's like a whole number. It just looks nicer. You could have made it 1,000, they decided to do 100. That'd have been a lot more increments if you did 1,000. And then he made equal increments along the way, so that each degrees is the same difference. Okay, there's not like 1 to 10, and then once you get to 10, there's a jump in the amount of what the actual, difference in the amount of temperature there is. He didn't do that. He made it constant. So it's 1 degrees. So then he did 0 to 100, 1 degrees, and he made 0 freezing and 100 boiling of water at 100 kPa. So that's what Celsius is. The Kelvin is more. It's used by people who do chemistry, not people who do it just every day, or other stuff. It's just he said they came up with the point of Kelvin is the point at which they made 0, right? They made 0 Kelvin. They define this as the point at which they believe. I think they've proven it, but they believe that I don't know for sure if they've proven it, which all molecules have the minimum amount of energy that is possible in the universe. So basically what the universe wants, at a certain point, you go down on a certain point. This is where a molecule like water, which I've gone over before, like water, I'm not going to draw it all out. Water has the minimum amount of energy that it can, okay, as a molecule. Like in terms of moving this way, like it's moving. In terms of like moving around, it has the lowest possible. And they define this as 0 Kelvin for all molecules. And then they gave remember I said they could make the interval however they want. They could make it the same throughout, or they could have jumps if they want. It's whatever system they want. Well, they made the interval be the same length as for Celsius. So this is why you can actually easily convert Kelvin to Celsius, because the interval is the exact same. So if you have 100 Celsius, right, that's the same as 373 Kelvin, and it's because it's an equal interval. Okay, and it means that water feels cold, right? But the fact is 0 degrees Celsius, with the point at which water freezes, right, at 100 kPa, right? Okay, this is actually, in terms of the lowest amount of energy that water can have, it's actually at 273, above 273 intervals above the lowest possible energy you can have, and that's occurring when it's at 0. Okay, so it's cold at 0, but the minimum amount of energy it can have, you can see that difference is 270. It's like if you lowered it, it'd be negative 273 Celsius. Okay, that is what it is. Okay, because you go because it's same interval, you go from 0 and you go down, you keep going down to 0 Kelvin, right? That's negative 273 Celsius. So that's the lowest possible energy a thing can have. So that's interesting. So you're going to see Kelvin a lot of places, okay? Almost everything. That's just what it is. So basically, this is going to be, we're going to look at the interaction, okay, between water and ethanol. Water, and most people draw this, water and ethanol, okay? That's what we're looking at, right? If we're looking at water and ethanol and how they interact, right? So water. First, it is not really the most important, but it's good to know how things interact, because if you can see what the interaction is going to be, right? We went over last video, hydrogen bonding, polar, London, right? You can see what the interacting is going to be. You can see when things interact more, there's usually more of a change between what pressure and temperature. They'll become liquid and gas, and how much of it will become liquid and gas. There's usually more of that change, better interactions there are. Okay, so we have water and then we have ethanol. So ethanol is an alcohol, which just means meth-eth, right? So meth-ethanol. This is ethanol, okay? You can see here that there's a bond here, which I'm going to draw. You almost always draw ethanol like that, hardly ever not drawn like that. But I'm going to draw it to look like kind of the same drawing of water. Okay, here to O, and then you might notice, this is ethanol, right? You might notice here, what's this? Oh, we have another one of these bad boys. Another one of these guys. Forget I said that. Another one of these guys. Like this. Which is the same here. So what happens between water and ethanol? Well, you get hydrogen bonding between water and ethanol. Okay, we went over last video. Alright, so you have the polar interaction, but because it's hydrogen, it's very strong. Okay? We went over this last video. And it's hydrogen and water to oxygen. So that means that these guys, this is going to interact very strongly. When you mix water and ethanol, they're going to interact together very strongly. Okay? Very strongly. Very, very strongly. Okay, it's wild how strong this is. Okay, so because of that, and actually we'll get into it, but there's a point, for a lot of pressure temperatures, you can separate these, right? Because they're connected by interaction. So this, right, I went over my last video, this isn't as strong as an actual bond. And you can separate some things that are connected by this. You can separate things that are connected just by interacting. But there's actually a point at which this interaction, for the certain pressure and temperature that you're at, this interaction is so strong that you can't separate these. Okay, just by changing the pressure and temperature. Because this gives of the hydrogen bonding. How would we plot this if we have two things? How do we plot that? Like what do we put on the axes here? Do we do a third axis, and do we put a third axis? And do we put water here? And do we put ethanol here? Like how do we make this plot when there's two things, right? And we want to do this. And then how do we, as well, if we have pressure and temperature, how do we show what's going on out of pressure and temperature for these, right? For two things. How do we plot that? Well, the way that they most commonly plot it, there's tons of ways they could actually plot it. There's so many ways. But the way that they decide to do it, okay, this is the way that most commonly seen, is they'll put either pressure or temperature here, and they'll say that this plot will be the data will be provided for changing temperature, right? It changes, and one pressure. Okay, so let's say pressure of 100 kPa. So most commonly, you'll see that, because like, how do you plot it? There's so many ways you can plot it. Most commonly, they'll put the changing temperature, and then they'll put like one pressure, or the opposite. They'll be changing pressure, and they'll put one temperature. Because if you're going to show something with just two axes, you have to show you can't show as much data, right? You can do other ways. You can do 3 dimension, or you could even do 4. You can't really do 4. You can do 4. You just change the increments. Okay, so there's different ways to do it. So that's how they most commonly do it. And then for this, how do they show two things? Well, they do it in a clever way. And there's other ways you could do it, but they do it in a clever way where they say, okay, well, if you have water and ethanol, let's say you have 1 liter of water in ethanol, right? It's ethanol, right? And then it's 50. Let's go with 90 volume % water, right? And 10 volume % ethanol. Okay, so that if you do quick math, that'd be 900. Says 90 volume %, 10 volume % ethanol. So that'd be 900 mils of water and 100 mils of ethanol. That's okay. You don't even need to do that math. Yeah. So then, because that's true, right? what that means is you can say that the amount of ethanol equals the total amount of ethanol in water, right, which is 1 liter, right, minus the amount of water, right? Because if there's only two things, you can say that the amount of one thing is equal to the amount of the total minus the amount of the other thing. So that's what they do. So basically they'll plot one thing here, okay? So, and then they'll plot one thing here. So let's say, and they usually plot it in mole percent, but you could do volume percent. You can plot data however you want. It's just some ways are easier than others. But they choose to do mole percent. So they'll tend to do mole percent of ethanol, okay? Boom. And they'll plot that. So what that means is if you have 50 here, right, which should be 0.5. Well, this isn't actually mole percent. This is a mole fraction. So let me delete this. So if you have 50% mole ethanol, obviously, if the other thing is water, you have to also have 50% water. Or if you have 75%, right, 75%. Ethanol, right? Obviously, the other thing has to be water. So it'd be 25% water, because it'd be 100%, which is the total of ethanol and water. And then you'd remove the amount that there's ethanol, and you get the amount of water. Okay? And then the same thing here. So you can imagine, in this case, what this would be, if you have 25%, then you would get 25% ethanol. The other amount has to be water, so you have to get 75% water. You have to get 100%, which is the total of ethanol, of water and ethanol. 100% is the total of water and ethanol, and then you remove the amount of ethanol, and then you get the amount of water, which is 75%. Okay, so we have for this. So remember with water, the line at which water existed as a liquid and gas was quite higher, right? At 100 kPa, there's quite a large amount of temperature. Because of that, the temperature at which you have partially liquid and partially gas is actually quite high. So we're not going to start this plot at 0, because it would be like 0, nothing happening, and then way up past 300 Kelvin, you would get stuff, right? If we start at 0, you'd get stuff at 300. So you have all this empty space, and I'm not going to do that. So we're going to start at pretty much where it starts, right? We're going to start at 350, which is pretty much where, at this pressure, we're at 100 kPa, pretty much the lowest temperature at which you have some of the liquid, some of the molecules existing as a liquid and gas at the same time. Okay, and then here we're going to put 374, which is about the high of it. Okay, and then here I'm going to put 100 and extend this. Okay, a little bit. Okay, so this is 100. Okay, so what it looks like, it's about this. It's about here, and then you just go down here, drawing this freehand. Oh, that's not good. It's about that. And this data, I mean, it's saying actually 101 ATM, 101 kPa. It's about the same. I mean, I'm going to put 101, I guess, but there's really no, it's pretty much the exact same. So we can see that, you can see at 101 kPa, we know that water boils at 100 Celsius, 101 kPa. 100 Celsius, as we said, is 373. Right, Kelvin. I said that already, okay? Right? Well, let's look. 373 Kelvin is like right here. Okay, and what we can see then is we're saying this is the mole percent of ethanol. So when this is at 100, it's all ethanol here. It's all ethanol. This is just ethanol, okay? Then, if we consider this is the mole percent of ethanol, if we over here, this is 0 mole percent of ethanol, which means everything has to be water. Doing what water does. This is just water, okay? And then what water does is at about 100 degrees Celsius, 373 kPa, water, liquid, and partially gas, which is what this data shows as well. It now becomes fully gas, which is at this point. You can see it's out of the point at this point at which water exists fully as liquid and partially as liquid and partially as gas. Okay, so that what we did in the first video is still in this data. It's just because ethanol and water interacting, and they interact very well because of the hydrogen bonding. There's just the pressures and temperatures at which partially a liquid and partially a gas changes, right? And it changes with the amount of each that you add. It's very interesting, isn't it? This is cool. It's cool stuff. Okay, so now let's look at this. So let's say we added 50% of each, right? 50% of each. Well, if you add 50% of each, and we only increase temperature to like 355, right? Or I don't know exactly what this temperature is because I just drew it relative, but let's say we increase it to here, right? Well, at this point, as you might guess, based on the water, this point is where when you put these two things together, when molecules are both liquid. The molecules of everything that you put together that are interacting are both liquid. Like I said, they're only interacting, right? So you can separate, but because they're interacting and they're different things and they're interacting pretty strongly, that's what causes the different properties, as opposed to when they're just by themselves. That's what causes the different properties. Okay? So we have liquid. This is liquid. And then this is gas. Okay? And then this is both. Okay? This is both in here. I'm not going to... Oh, yeah, okay. I'll write it. Liquid. Right? So that's so cool. So, now let's say we get to... Let's increase temperature. Let's say we add 50%, right? And we increase temperature to here. Well, now we're at the point where the interaction exists as both a liquid and partially as a liquid and partially as a gas, right? The interaction exists as partially liquid and partially a gas. Okay, let's say that we want to. Well, now if we were to increase temperature further, we'd end up here, right? And this is all happening at 101 kPa. All right, so if we increase temperature further. It all exists as a gas, right? That's it. It's really that simple. People have gotten the data for this, so it's really that simple. The interaction, depending on the pressure and then the pressures and the temperatures, the interaction exists as either a liquid or a gas, or partially liquid and partially as a gas. So that's it pretty much. Okay, so that's pretty much it for this video. I'm gonna try to make these videos shorter. So the next video I'm actually gonna go over. Let's say that you want to. If you're at this point, right? You're here. You want to figure out the interaction, right? Because partially exists partially liquid and partially gas. So you end up with, let's call this molecule. Remember, I used A last time, so I don't want to confuse. So I'm going to call water. A1, okay? And I'm going to call ethanol A2, okay? Because they're both polar. If you can see, they're both polar molecules. So I don't want to give it B because I gave B last for non-polar. So A is water, and A2 is ethanol. Okay, so we're going to give it. You have this, right? You have A1 interacting with A2 when you actually draw the structure of the interaction with A2, which will be interacting with A1, which might be interacting, because A1 can interact with itself, or it can interact with 2. You have interacting here, right? And then you end up with interacting here, right? So you end up with, it's another structure, and because of the hydrogen bonding, you end up with a very strong, a structure that's interacting with itself a lot. A structure has a lot of interacting, okay? Right? Because of the hydrogen bonding. So you end up with this. So then you want to say, okay, we're at the different pressure and temperature, how much of this interaction, right, of these interactions are existing as a liquid, okay, as a liquid. And then, right, and then how much of these interactions are existing as a gas. Like how much? We see that at this pressure and temperature, it all exists as a liquid. We see at this pressure and temperature, this interaction all exists as a gas. But when you're within here or on the line, we can see that this interaction exists partially as a liquid and partially as a gas. So you want to say how much of the interaction. So let's say you have one mole of this, right? Well, how much of that mole is existing as a gas, and how much of that mole is existing as a liquid? So if say you want to know that, right? You can know that you can do that. But let's say you also want to say we can see here, right, that the structure is interacting, but these are only interactions. They're not full bonds, which means that you can separate these two. And given the pressure and temperature, you can actually end up separating these such that the amount of water that exists in the liquid and the amount of ethanol that exists in the liquid versus the amount of water that exists in the gas and the amount of ethanol that exists in the gas aren't identical. Okay, so it's not like these are interacting completely as one new molecule, right? They still have some properties of their individual molecules, even though they're interacting, right? Yeah. So that means is that you won't exactly end up, let's say you have 50% ethanol and 50% water. That doesn't mean that once you reach partially a liquid, and you end up here and you have partially liquid and partially gas, that doesn't mean you'll have an equal amount of water and ethanol here and an equal amount of water and ethanol here, right? Because just because you have the same amount of water and ethanol, that's not that. So because of that, just because let's say you have 1 mole of, let's say you add 10 moles total of ethanol and water, so you have 5 moles of ethanol and 5 moles of water, that doesn't mean that here you're going to end up with the same amount of moles of ethanol and water that are liquid and the same amount of moles of ethanol and water that are gas. You might end up with more here than ethanol and more here of ethanol than water, okay? Or the others. We'll see what occurs, but I think we, if you've ever, I don't want to add too much of this, but if you've ever seen ethanol, you can smell it quite strongly, and it evaporates quite well, which would lead you to believe that it exists as a gas more easily at this pressure, because that's the pressure that's around us. That, right? That you would notice that. So that means that at this pressure of ethanol exists more likely, it seems that it more easily exists as a gas than a liquid compared to water. So that would be my instinct. That's what I would think. But we'll see. We'll have to see. Okay, that's everything. So thank you. Yeah, I guess I'm going to try to make less, how do you say that, shorter videos. Yeah, that's everything. Thank you for coming.